Today's lesson is on growth and decay, which are really just application problems of differential equations. When you read a problem and it tells you the rate of change is directly proportional, you know you're talking about y is equal to k times x. If it's inversely proportional, it's y is equal to k divided by x. So let's read our first problem. The rate of change of p with respect to t is proportional to 10 minus t. Find the function. It's proportional, so we know it's that. The rate of change of p with respect to time is proportional, that's where the k comes from, 10 minus t. Then we're going to integrate both sides because it's a differential equation. Oh, bring your dt over here. And you end up with p is equal to k times 10t minus t squared over 2 plus c. The next one says the rate of change of n with respect to s is proportional to 250 minus n. Find the function. Be careful when you read this. I've screwed it up 3 times already. The rate of change of n with respect to s is equal to k times 250 minus n. Remember, you want to get your variables that are the same on the same set of equations. You separate them. So you have to bring this over here. You have 1 over 250 minus n dn equals k ds. And you integrate. Do a u sub again so you don't forget the negative. 250 minus n. When you find du, you get negative 1 dn. So this becomes negative ln of 250 minus n equals ks plus c. Let's move our negative over. So you have ln of 250 minus n equals negative ks plus c, e to the power, and you get 250 minus n equals c e to the negative ks. And from there you can solve for n. All right? It says the rate of change of y is inversely proportional to y, the rate of change of y. So dy, dt, the rate of change, so it has to do with time, is equal to k over y. You have to bring your y over to this side, y dy equals k dt, integrate, y squared over 2 equals kt plus c. You multiply by 2, y squared equals 2 kt plus c, and then take the square root. And since we don't have any initial conditions, you keep the plus or minus. This one, the answer should be y is equal to kt over 2 plus c squared. See if you can get that. All right. In many applications, the rate of change of variable is proportional to the value of y. And you get the equation y is equal to c e to the kt. That's what we got up here. And we'll work through one of those so you understand where that came from. C is the initial amount. K is the proportion constant. If it's positive, you're growing. If it's negative, it's decreasing. This is a formula from Algebra 2 when you did growth and decay and in pre-cal. The steps are the same. You separate your variables, integrate, solve using the initial amount, solve for other missing parts, and then solve for C. All right, so let's do an application. The weight of a population of yeast is given by a differentiable function y, where yt is measured in grams and t is measured in minutes. The weight of the yeast population increases according to the equation dy dt equals ky, where k is a constant. At time t, the weight of the yeast is 144 grams, and it's increasing at a rate of 24 grams per minute. Write an expression for yt. All right? So they told us that dy dt is equal to ky. And originally, the original rate was 24, and the original weight was 144. So you end up with k is equal to 24 over 144 which is equal to 1/6. If I integrate this function right here, integrate dy dt, no, first I have to separate my variables, so I have 1 over y dy equals k dt. All right, you integrate, this is ln of y equals kt plus c. Raise it e to that power, and you get y is equal to c e to the kt. That's where that equation came from that we were talking about on the last page. All right, now we can plug in the information that we know in order to find c. We knew you had 144 to begin with. C I don't know. EK we just solved up here is 1/6 t. Plug that in your calculator, figure it out, and you get that C is equal to 144. So you have y is equal to 144 e to the 1/6 t. Well, this was 0 too. Which makes sense because that's supposed to be the initial amount. Okay? This is really appropriate. During a certain epidemic, the number of people that are infected at any time increases at a rate proportional to the number of people that are infected at that time. If 1,000 people are infected when the epidemic is first discovered, and 1,200 people are infected 7 days later, write the equation where there are 12 days after the epidemic is first discovered. Okay, so what do they tell us? They told us the rate of growth looks like that. We know that equation ends up being this. C is my initial amount, so I go ahead and plug in my 1,000. P is what y is in this case, so you have 1,000 e to the kt. One of those things you just sort of remember. If you don't, you go back like we did here. You bring p over, you integrate, you get ln of p, and solve it. Okay? Now, let's use the data they gave us. There's 1,200 infected after 7 days. So 1,200 equals the initial 1,000 e to the k times 7 days. And I have to solve that. I end up with 1,200 divided by 1,000 equals e to the 7k. Take the natural log of both sides. Equals 7k. So k is equal to 1/7 times ln of 6/5. To write the equation for 12 days, you have y is equal to the initial amount. E, put in your k value, 1/7 ln 6/5 times 12 days. You can leave k. This is fine. I don't have a calculator. All right. Let's do one more, then I'll give you the answers to the AP questions. Okay? Your tires have just run over a nail. The air is leaking out of your car's tire at a rate of change of the air pressure inside the tire is directly proportional to the pressure. So, you know, the rate of change of pressure over time is Kp. They gave us the initial one decreasing at a rate of negative 0.28. K times 35 pounds was the pressure to begin with. So K is equal to negative 0.28 divided by 35, which is negative 0.008. Solve the initial, subject to the initial conditions. Well, we figured this out right here. So it's the pressure in the tire is equal to the initial, well, it's one of these, C e to the kt. The initial pressure is 35. We just solved for K, which was negative 0.8 over 35 times T. If you were going to sketch that, at time equals 30, it's here, is an exponential function with a negative exponent. It's decreasing. It's going to go to 0. Okay? Back here doesn't really matter because there's no negative time. What would be the pressure 10 minutes after the puncture? Let's make it a P. Pressure is equal to 35 e to the negative 0.28 over 35 times 10, and I got 32.309 psi. And then it asks us, is it safe to drive the car? The car is safe to drive if the tire pressure is 12 psi or greater. So how long after the puncture will it be safe to drive? You have 12 equals 35 e to the negative 0.008 t. You divide by 35 first, and then take the natural log of both sides. So I get t is equal to 35 over negative 0.28 times the natural log of 12 over 35, which is equal to 133.8 minutes, which is approximately 2.23 hours. Not bad. Okay. These two problems are AP questions. The answer to this one is B. See if you can prove it. The answer to this one is B. See if you can also figure that out. If in doubt, go to the PowerPoint. Thanks for listening. Have a great week.